Good morning. I'd like to thank you for the opportunity to speak this morning and to share the technology that we're developing with ClearStack. I'd like to give you some background and with my background, I tend to be a little bit too technical, so I'm going to try to not spend too much time dwelling on that, but to also focus on the opportunity that we have and the innovation that's available, that's being developed. I appreciate Monty's slide with the Vikings going off to battle. I think that's something that we all face with technology development, that we want to use technology that was proven 50 years ago and be the fourth or fifth group to use the technology and not be the first one. And so that we face that same situation. So if we can pull up the slides, please. So what I'd like to talk about today involves where we are with the technology development. First of all, what we can do, the deliverables and the efficiencies that are achieved with the technology. Talk some more about the specific pollutants and some of the opportunities and how we achieve these pollutant removal efficiencies. And then there's some other benefits that I'd say it kind of fits into the miscellaneous category, and then finally wrap it up with an update on where we are with our development and where we plan to go with that. So this is kind of a summary slide to help capture the main overview of what we're able to achieve, and what's been demonstrated, what's been modeled, and that sort of thing. Basically, the way I have it broken up here on this slide is in three different categories, basically based on the mechanisms that are involved. The first one involves the staged combustion of the coal, and this technology, just before I forget to mention this is primarily based for coal-fired power generation units, and so there's plenty of those in the United States, and it's especially an interest for this region of the country in the use of coal-fired power. But one of the opportunities and advantages that we have with our technology is we can utilize this as a retrofit technology to basically put staged combustors on the existing coal-fired units in replacement of the coal burners that are there currently. And what I'll be focusing on is a T-fired unit, which is pretty popular in this part of the country. And basically, by putting the staged combustor on, we are able to keep the stoichiometry in low regions during the initial parts of the reaction when the temperatures are higher, and by doing that we're able to minimize the NOx generation, and that's obviously a major issue with regional haze regulations. And so what we're able to see and able to demonstrate is a major reduction in the NOx emissions from the standard pulverized coal-fired unit, and so that's a major advantage for what they're required to achieve in the regulations moving forward to continue operation. The carbon monoxide is not necessarily as big an issue but for regulations, but it is something that is a benefit, so that those levels are kept very low also by the same mechanism. The second mechanism I want to talk about, and this is something that's unique to our technology, is what I'll show is that we inject pulverized limestone in with the pulverized coal, and by doing that in the reducing atmospheres of the combustor, we're able to have the reactions that are preferentially capturing both the sulfur and the mercury, and this is also a major advantage of our technology for some of the big regulations that we face. Sulfur is a big issue in some parts of the country, and so by keeping the sulfur in the reduced form, it doesn't generate SO2, it's still in the elemental form, and there's a preferential reaction for the calcium to capture that. That comes out in the slag in the bottom of the combustor, and the mercury also does that. So it's vitrified and it's captured basically in little glass BBs. My boss has a little vial of these slag pellets on his desk for future demonstrations and illustrations. But basically, just before I finish up, I wanted to mention, finish up with this slide. I want to mention on the diagram here is maybe a way to look at it. We have 3 stages of air. We have the air that comes in with the limestone and the pulverized coal. That comes into the combustor, and it's about a 0.6 stoichiometry, and that allows the reactions that we need and the temperatures to be accomplished. And as the flue gas is exiting the gasifier, or the syngas actually, the gasifier or the combustor, a second stage is added as it goes into the boiler. That generates more heat as it reaches a 0.9 stoichiometry. Then as the gases go up the boiler, and this is especially going to be easier to do with a T-fired boiler because of its height, then the temperatures are dropping, and then to an acceptable range to avoid NOx generation. So we're able to add the third stage of air and then complete the combustion and achieve about 10% excess air, or 110 or 115% stoichiometry. So anyways, I want to mention that before I get off of this slide. So that's kind of the basic arrangement with the air input. As far as the categories of pollution control, the final one I kind of consider to be the miscellaneous category. We have particulate removal that's very significant compared to a existing pulverized coal unit, and I have a slide for that I'll talk more about. Air metal toxics and acid gases are significantly reduced, and then the slag and the ash passes the EPA's T-clip test, and I've got some data on that from past demonstrations. And then finally, it has minimal auxiliary power demand. By capturing the sulfur with the limestone before the boiler, as opposed to a scrubber in the flue gas out after the boiler or post-combustion, we're able to avoid a major source of the pressure drop that has to happen in the scrubber and the auxiliary power demand that is required for the recirculating pumps for the scrubbers. So that's one of the advantages that we have. So overall, it gives a more favorable heat rate for the boiler, which means improved efficiency overall for economics for the utility, and also reduces the CO2 emissions per megawatt of power that's sold to the grid. So that's some of the advantages that we have. So that's a whirlwind summary, and I will try to break that down a little bit more in detail. First of all, we had CFD modeling done by Alstom, which is now GE, for a 85 megawatt T-fired unit at Hudsonville. Was owned by Ameren at that time. They were interested in our technology, and so the engineering work was being done for this boiler. And basically what this shows, there's 2 slides out of the hundreds that they developed from the modeling, but that I wanted to point out the NOx and the CO emissions that we had talked about earlier. Basically, the NOx emissions were significantly reduced and were very, very close to what we were able to demonstrate with a smaller pilot unit. So it's 0.095 pounds per MMBTU was achievable, which is very favorable for most permitting requirements. And then the carbon monoxide was down in the 7 to 8 part per million range, which is also very, very good. So this gives you some idea of some modeling that was done. What it also does, if you look at the boilers, you can see the combustors mounted on the corners as you would do for a T-fired unit. And basically, like I was saying before, you take the coal burners off and put in the same basic boiler opening, you would put these combustors. And for this particular unit, they found that because of other building steel and existing equipment in the boiler building, they had to look at just putting in 3 combustors instead of 4. And there was, based on the modeling, there was adequate circulation and it was acceptable. So that's why you actually see just 3 out of the 4 corners there. As far as the NOx generation, there's various kinetic modeling that can be done and has been done. This was done by EER, basically looking at the response of the NOx concentration generated, or the emissions, based on the second stage stoichiometry. And once again, that's the air added as the syngas is going into the boiler. And this further confirms what we've been able to experience through other methods and other approaches, including the pilot demonstration, that basically when you get down to about a 0.9 stoichiometry in the secondary air or second stage air, you're able to get down below 0.1 with your NOx emissions. So that's very favorable. At the time this was developed, a lot of the people were facing much higher NOx emissions. So this is very significant reductions without having to put in a SCR or other types of post-combustion controls. Talking about the sulfur removal, what this diagram shows is our experience and what we were able to demonstrate with some of the pilot units. There's basically 3 dots on this line on the right side, and then a fourth one to the far left. The 3 dots on the right side are demonstrated points that we've been able to achieve with the pilot units. The 2 to the right are demonstrations that were done at Foster Wheeler at their demonstration pilot unit, and I'll talk about more about the size of those units. But basically what this shows is that when the limestone size, the particulate size was about 200 microns average, we were able to achieve about a 36% removal of sulfur. By going to about 100 micron size, we were able to achieve close to 45%. And then the more recent demonstration that we did at the Lincoln demonstration unit that we did in Illinois, we were able to achieve 30% reduction in sulfur. So we see a very direct relationship, and I think that basically has to do with the available pore volume in the limestone, and so we want to take advantage of that. The current project that I'll talk more about in a little bit, we're looking at 10 to 15 micron limestone, and so that's very fine powder, but that gives us, I think, a very good advantage with the sulfur removal. So that's why this kind of gives you another viewpoint or aspect or perspective, I guess, of why we think we can achieve at least 90% sulfur removal, and this is without the need of a scrubber. As far as the particulate matter removal, there's 2 main mechanisms here that I want to point out, and the first one is in the table. If you look at the middle of the table, you have the conventional coal-fired boiler. You have particulate matter in the fly ash that you can demonstrate or measure the size distribution. And the issue that you'll face with a typical boiler is that you have quite a bit of the small material that's PM5 microns or smaller. It's very difficult to remove in an ESP, which is the conventional or standard control technology for particulate matter. And so basically you have that 65% efficiency. That's not a very high efficiency of removal. And with our technology, because of the high temperatures and the slagging tendencies in the combustor, you have an agglomeration of the particulates, making the particles larger, and makes it easier for removal in the ESP. On top of that, before you even get to the boiler, you have about 60 to 80% of the ash removed as slag, and so you have this combined effect of removal of ash in the combustor, and then what's left going to the ESP is removed at a higher efficiency. So if you do the math for the combined efficiency improvement, you're talking about roughly a 96% reduction versus what you would have now with just a standard coal-fired unit with an ESP. So just wanted to kind of go through that. Some of the other mechanisms that are also working in our favor is we expect to have lower flue gas velocity because of lower excess air in the boiler, and that will help remove more particulate in the ESP. Lower velocities mean more removal. And then also there would be less condensable particulate matter. I don't think that's as much of an issue in this part of the country, but some areas that's an issue, and by removing almost all of the sulfur, then you have less condensable matter after the fact that may contribute toward your regulations. What I would like to also talk about is it kind of fits in my miscellaneous category for benefits. We've seen a lot of news with Duke and TVA and others that have had issues with ash pond leakage or spills and that sort of thing. And one thing that our technology is able to do, because of this vitrification and capture of the metals and the different pollutants in the slag and the fly ash, is that these materials are actually acceptable for use in cement manufacture and asphalt. And so by not having the leaching issues that you would have with some other forms of ash and slag, you're able to have a broader market. Instead of putting the slag and fly ash in a pond, you're able to actually send it off to cement companies which are looking for the higher grade cement products. And so what you see here is 3 columns, or four columns actually. We have the element that's tested and evaluated, and then the results from the fly ash and slag samples that we collected from our demonstrations that we've done. Actually went out and got samples and had them sent off to a lab for testing, and then the regulatory limits that's part of the TCLIP requirements. And basically what they do is they pour a mild or a dilute acid through these materials, look at the filtrate afterwards, and then calculate the concentration in milligrams per liter. And you have to meet these requirements on the far right column. And as you can see, we're easily meeting those requirements with the demonstration that we had done. So anyways, that's one of the advantages that we have also that can help with the ash pond issues, not only for the cost of maintaining an ash pond, but also the liability of issues down the road that may occur. So this is kind of the written summary of the technology benefits, and basically this is truly a multi-pollutant technology. It's not something that would only pertain to one pollutant. There's lower cost than post-combustion alternatives. I don't have a lot of numbers in here, but I can provide that later. But basically, it's about a third the cost of having to put in an SCR in a scrubber. So it's beneficial that way. As I just finished talking about, we can convert the combustion byproducts into a sellable sales stream, revenue stream. We also avoid the use of costly and hazardous reagents that you may have to use in a scrubber or SCR, so you don't turn your utility into a chemical plant where you have all those disposal issues and handling issues. And then finally, this is somewhat of an intangible type thing, but we're dealing with public impressions, and that sort of thing is as important as ever. You don't have the visible water plume that comes out when you have a scrubber. So you have the dry stacks, and that's basically where our name came from, the clear stack, that you don't have that plume coming out that people would say, well, look at the smoke. Well, it's not really smoke, but this no visible plume from that kind of from having a scrubber. So just kind of talking about our technology development, kind of where did it come from, and then where did we go to get where we are now. Basically, the initial concept came from Germany in World War II when they were cut off for their supplies of the petroleum products. They had to produce their liquid fuels from other processes, and specifically their own brown coal. And this is an alkaline coal, so they were able to run their gasifier without adding limestone, and they were able to get the performance that they did without adding the limestone. That was an oxygen-trained gasifier or combustor as opposed to ours, and they were able to actually capture 70% of the sulfur. where our company got involved, and the developer of this technology started out was when he was working for Florida Power, and they were developing this technology, and they did the Foster Wheeler development that we talked about with the sulfur SO2 capture slide, and they were able to achieve 45% sulfur capture and improvements in NOx generation. And then Florida Power lost interest in developing this technology, so this technology was basically spun off on a separate company. So then ClearStack was formed in 1998, and then another demonstration was done, and that was the Lincoln facility that I had talked about, and we were able to demonstrate quite a few of the facets that I was able to show you previously. And once again, it's air-entrained gasifier or combustor with 2 stages prior to the boiler, and then a 3rd stage in the boiler, which is basically where the overfire air is existing in many of the newer boilers now. Just to kind of wrap things up, I just want to show you some diagrams and to kind of give you an idea of what our status is. We have kind of a parallel path development going on right now. First of all, we're looking at pilot scale demonstrations. We're talking to both GE, and this is what is shown on this diagram. They have a 40 million BTU demonstration facility, and then some other ones that we're also talking to. And basically the idea here is to take the specific coal, and this would be in our case what we're developing right now is a Western coal that we want to run through the gasifier as opposed to the Illinois coal that had been developed before, and to just document the emissions and that sort of thing. We believe that the Western coals will have better NOx emissions. We just don't know exactly how much more, so we believe it'll be good to be able to demonstrate that with actual operating data. And then once we have this pilot unit in service and available to use, then we can bring in other coals from other seams, other locations for other potential applications, and be able to use that for future customers and that sort of thing. So that's one avenue that we're working on. The second one is we're working with a Western power generating utility, and we're looking at a unit that's 300 plus megawatts, T-fired unit, and looking at doing a retrofit there, taking out the coal-fired burners or coal burners and putting these combustors on each corner. And basically what you see with the orange is just to highlight the new equipment. There's not much of a footprint compared to some other technologies, so we have to put in a limestone silo with a feeder to blend the limestone in with the coal, and then put the combustors in each corner, and then have a little slag quench pots or tanks underneath each one to quench the slag with the water. And that's most of the new equipment that would be required. And then the blue equipment items are indicating what would be removed, bypassed, or reduced. And in this case, there's a booster fan that wouldn't be necessary to use if you didn't have the scrubber in place, and the scrubber itself could be bypassed. And so we actually have a reduction in the footprint that's capable. So, okay. So just to wrap up, and it's worked out pretty good, I think, timing-wise. This kind of gives you another perspective of this unit with the combustors installed on there. A side view showing how they would be attached, and the top view showing how the combustor would have a swirling tendency from the tangential entry, and then the syngas would go into the boiler. And then to wrap it up, just as summary, we provide a multi-pollutant technology, and working both with pilot and commercial units. And if you're interested in more information, I'll hang around afterwards. But we're excited about where we're at now. We're actually moving forward with quite a bit of interest from some of the utilities. Thank you.